Our last video showed the isomorphic or equal-shaped relationship between the group of symmetries of an equilateral triangle, D6, and the group of permutations of three objects, S3, and how this relationship was described by the homomorphic equation. So we called these two groups isomorphic. In this video, we will explore some of the characteristics of the isomorphism and how we can use that in the study of group theory. Recall our homomorphism equation. Now, let's show that our mapping phi from D6 to S3 is a bijection. It is both one-to-one, we call injective, and it is onto, which we call surjective. Let's look at what each of these mean. Phi is one-to-one. Each of our elements in the domain is mapped to a unique element in the range. No two elements from D6 end up mapped to the same element in S3. A benefit here is that we get an inverse function, a map that can take us back to the original group. The reflection R goes to the transposition 1, 2, but we can also go back from the transposition to the reflection. And for this to hold for the entire group, there must be as many or more spots or elements in S3 for all of the elements of D6 to be mapped over 2. So all 6 elements from D6, E, A, AA, R, S, and T, have a unique place to go in S3. Second, since phi is onto, something will get mapped to each and every element in the range. No element will be left unused. Remember our previous example Z12 to S2? We mapped even elements to the identity and odd elements to the transposition. Since the only two elements in the range were the identity and the transposition, that map was also onto. However, the two groups were only similar shaped, not equal shaped. For something to be onto, there must be as many elements in the domain to cover all of the elements in the range. There must be enough elements to get mapped to each and every element in the range. So how can there be as many or more elements in S3 than D6 for us to be one-to-one? And at the same time, for us to be onto, there must be at least as many or more elements in D6 than S3. Well, this can only happen when both D6 and S3 have the same number of elements. So, the first characteristic of an isomorphism, the mapping is both one-to-one and onto. We call this a bijection. And we know that two isomorphic groups must have the same number of elements in each group. Remember, under our mapping phi, we will get the same answer if we perform the operation in the domain and then map that answer over to the range, or if we map the elements from the domain over to the range first and then perform the operation on the elements in the range. One thing we observe, if the identity is involved, then performing the function in the domain, of course, just gives us the same element. In other words, alpha star identity just leaves us alpha. And if we map that answer alpha over to the range, we see that the only way the equation works in the range is for the identity to get mapped over to the identity. This is, of course, the identical argument we make for identity star beta. Our answer on the left would be just beta. And then we map that answer, phi of beta. And the right side could only be true if the identity maps to the identity. So, our next characteristic of the isomorphism is it will always map the identity in the domain to the identity in the range. Given the element in D6, the reflection about the 150-degree axis we call the element S, S has an order of 2. It is its own inverse, and thus, in our equation with alpha and beta, S follows S on the left side is just the identity. We also know that S maps to the transposition 1, 3 in S3. Notice on the right side, if we perform the element 1, 3, we see the only way to return to the identity on the right side is to again perform the element 1, 3. So we see that in this simple case of a transposition element, since it is its own inverse, the inverse of S on the left actually maps to the inverse of S on the right. And we can check out if perhaps all inverses map to inverses. We know in the set D6 that A and AA are inverses. We can perform the rotation of 120 degrees, the element A, and then the rotation of 240 degrees, the element AA, and we get back to the identity. With A mapped to the element 1, 2, 3, and performing element 1, 2, 3 on the right, we can see that the inverse, the element that will take us back to the identity on the right, is the element 1, 3, 2. And so we see, because AA maps to 1, 3, 2, the inverse element will again map to the inverse. Again, without mathematical proof, but hopefully through intuition, we hope you can see through these examples, or even through a basic inspection of the equation. For an isomorphism, the inverse of an element in the domain will always map to the inverse element in the range. And that is the final characteristic of an isomorphism we will show. Inverses map to inverses. Now let's recap. First, isomorphic groups must have the same number of elements, which makes sense if you're going to say that they're equal shaped. But there must also be a bijection, a map or function from the domain to the range that is both one-to-one, where each element is mapped to unique elements, and onto, where all of the elements in that range have been mapped to. Really, All of the elements from either group is mapped to all of the elements in the other group. In that mapping, the identity element will always be mapped to the identity element. And finally, an element's inverse will always map to the inverse of that element's image. An inverse gets mapped to inverses. In this video, we showed some of the characteristics of an isomorphism, a bijective mapping between two groups where the identity is mapped to the identity and inverses are mapped to the inverses. In our next video, we will cover some of the different group representations and make a powerful statement about isomorphisms to a group or subgroup of the group of permutations. We hope to see you in that video, and if you like these videos, please give them a thumbs up or comment down below, and help the channel grow by telling a friend or becoming a subscriber.